Hello, everyone, and welcome back to the workshop PWF Sudan. So, today we will have a lecture about the introduction to density functions theory. This lecture will be given by three members of the group of Michele, the research group. Uh, so today we welcome Nikit, postdoc in the group. Valeria she's a PhD student, and also Fabrizio, he's a postdoc. They they their research focuses on the electronic structure methods and methods development. So please welcome, and you can share your screen now. Okay, we cannot hear you.
Can you hear us now?
Yes, we can hear.
Okay. Yeah. How do you put full screen? How do you?
I don't. Yes.
Yeah. Can you see our screen now?
Yes, we see.
Okay. Hello everyone. I'm Aniket. This is Valeria. We also have Fabrizio.
Hello.
Yeah. And so we are from Rutgers, Newark, and today we're going to be giving a brief introduction on DFT. Thank you to Musa for inviting us. Sorry that Michele couldn't be here, but we'll try to do our best in his stead. Okay.
I just want to say thank you very much for the last minute request. We really appreciate this.
Yeah, it's fine. We love talking about our research. So so DFT. So there are three primary goals of this lecture. The first is why DFT, what the theorems are, what the equations are. And the second part is something called basis sets, how we can use basis sets to solve our DFT equations, basically. And the third part is solving the solving the equation self-consistently, and that's the main. How does a computer solve the DFT equations? So okay, yeah, and we thought that there are some questions and some challenges in this lecture. I am sharing the GitHub link for the presentation in the chat, so anyone can download the slides from there. And we will have some challenges that the participants can do during the course of the lecture, and we will discuss the results and the solutions after the challenges. So yeah, the first thing is what are the interesting things that are being investigated in physics or physical chemistry in the real world? So like things like photocatalysts, nanoparticles, and these contain hundreds, thousands, and millions of atoms. So how do you incorporate the quantum mechanics of all these atoms and solve it in a computer. And so that's where these things called electronic structure methods come in, and they solve for the electronic structure of these systems. And these are a few flavors of the electronic structure methods that we have available. Now, this is a very minimalistic picture of the, but so basically there is a balance that is there. So the more efficient a method, the lower its accuracy, and vice versa. So you have the quantum chemistry wave function based methods, which are the most accurate, but they are the least efficient. So they take a lot of computing time. And for real world systems like photocatalysts and nanoclusters, it's virtually impossible to solve the electronics, solve for the electronic structure using these wave function based quantum chemistry methods. Now, something that's more efficient but less accurate is Kohn Sham DFT. And then there are more efficient but less accurate flavors of Kohn Sham DFT, of DFT, which is subsystem DFT, and then we have orbital free DFT. Now, all of these methods have their place in based on what system and what molecular properties they're being used to investigate. But all the while, there is this balance that's you tilt the scales in favor of either efficiency or accuracy based on which method you're using and which systems you're investigating. And so, yeah, so as I mentioned, we have the first challenge. So this challenge is basically to test your knowledge of the molecular Hamiltonian. And so, yeah, anyone with this, should we click it?
Yes, we can click.
So I can click and show you what the challenge is, but anyone with the slides can also access the link to the challenge, and it has a few questions. Which
the QR code.
Oh yeah, you can also log in using the QR code. That's over here. And access the challenge using the QR code that's here. And so, yeah, we take your time and we'll discuss the challenge once in like 5 minutes.
Yeah. We'll give you 5 minutes to solve the challenge, and then we discuss the solution of the challenge. We're also gonna see your answers, so please start doing it.
Yeah. Yeah.
Then I'll make this big.
Yeah.
Maybe they can react here. I don't know. Yes. So to make this a little bit more interactive, please put like a reaction in the chat that you were able to log into the challenge and you're solving the challenge. Where's the chat? Yeah, just put like a emoji, something like this, thumbs up, or any emoji, your favorite emoji.
Yeah, the challenge has points assigned, but no pressure.
Yeah.
We're going to discuss the challenge, the answers, and we're going to explain it.
Yeah.
Yeah.
Also, Fabrizio have shared the link for the challenge if you were not able to scan the QR code or download the presentation. How much time has it passed? 1 minute. Okay.
There have been responses. One response.
Okay, we have one response.
Yeah.
It's okay. It only counts the responses after they press submit. So.
Oh, okay.
Yeah, okay,
We can give them some time.
Mm.
Um, I have also noticed that the lectures in the main schedule, it's scheduled for 4 p.m. Sudan time. That is why most of the participants they still joining. But yeah, we informed them actually that the lecture is gonna be at 3, but in the main schedule it is scheduled for 4 p.m. But it's okay. Now most of them actually are joining.
Okay.
Okay, we are getting some results.
Yeah, yeah. Yeah, okay. We can go on and discuss what the challenges, what the solutions are, and we'll discuss a bit more. So the challenge kind of dissected and discussed the molecular Hamiltonian and the different parts of the molecular Hamiltonian, what kind of interactions are there in the Hamiltonian. And so this is basically the equation for the molecular Hamiltonian. And you see these three terms are T, VEN, VEE. So these three parts of the Hamiltonian and the ENN. So the first one, the T, is the kinetic energy contribution for any system of interacting electrons and a nuclei. The second part is the electron nuclei attraction. The third part is the electron repulsion term. And the fourth part is the nuclear repulsion term, which is if you have, it's in a molecule, you have more than one nucleus, you have the nuclear repulsion term. And so as you can see, the attractive term has a negative sign, and the repulsive term. So there's this balance that's there, a balance of the different types of forces that these electrons are nuclei are exposed to, and you combine all of these together, and then you can solve the Schrodinger equation for the ground state of this system of interacting electrons and nuclei. And so this is the Hamiltonian operator acting on the wave function of the ground state. And then you get the energy of the ground state as the eigenvalue, and the wave function is the eigenfunction, or the eigenvalue, or the, yeah. So the expectation values of each term of the Hamiltonian can be described in this manner. So you have the kinetic energy term, the electron repulsion term, and the electron nuclei repulsion term. Now keep in mind that all of these are functions of the wave function, but we can also describe them as a function of this term neta or n, which is the density. And so you can see that the electron nuclei term can be represented as a function of the wave function, can also be represented as a function of the density. It can also be written in terms of this potential. And finally, you can write this equation where it can be the energy of the electron nuclei attraction term can be written in terms of the density and the potential that of the potential. So that brings us to the question that since the energy depends on this density, is there more than one density that can give us this same energy? And that brings us to the Hohenberg and Kohn theorems, which discuss these in detail.
Yeah, so I'm gonna explain this part of the presentation. So as Aniket mentioned, we can describe a system not only with the wave function, but also with the density. And this was discovered by Hohenberg and Kohn. They found that the ground state density contains the same information as the electron density, the external potential, which is what has been referred as the electron nuclei interaction. And then there's a bijective map between them. Each of these functions is unique for any specific system. There is no other density that describes the system, and there is no other external potential that describes the system. So this can be also more, you can also dig more into this by reading the paper by Hohenberg and Kohn. So, okay, now we know that the wave function can describe the system as well as the electron density and the external potential. In this case, so in this way, we can represent the total energy as a functional of each of these functions. So a functional is basically a function where the main variable is another function. So that's why it's called functional. So in here we have the total energy functional that depends on the electron wave function. On the many-body wave function. We also can represent the total energy functional where the main variable is external potential or electron nuclei interaction, or a functional that depends on the density. In density functional theory, as the name implies, the main variable is the electronic density. And then, in this way, the total energy can be divided into the kinetic energy, that's a term that we've already discussed, the electron-electron repulsion, the electron-nuclei attraction, and the nuclear-nuclei interaction. Okay? So now let's go a little bit more deep into this, and let's do challenge 2 because we have seen the Hamiltonian, the molecular Hamiltonian. Now, what we're gonna do in this challenge is to write each term of the total energy functional in terms of the density or the wave function. So we're gonna give you another 5 minutes, so meaning at 9:42, we will discuss the solutions for each of this for this challenge. So please go ahead and start doing this challenge.
But I am also trying the transferability for other like
How many answers do we have? 0? Okay. We still have 2 more minutes to finish the challenge. Are you working on the challenge, guys? You have 1 minute and we haven't received any response. Okay, 1 response. Okay. Okay. Yes, we can see 1 response. Okay. So the time is over. Now let's discuss the solutions. There's only 1 response, and I think there's already a good idea on the answer. There's 2 responses. Okay.
Second one is.
Okay.
Yeah, it's in terms of sizing.
Yeah, okay. So what you realize is that the kinetic energy, let's discuss this. Okay, let's start for the electronuclei attraction instead of the electronuclei, the kinetic energy. Now, as we discussed with Aniket, the electronuclei attraction can be described as an explicit, it can be written as an explicit functional of the electron density. So far, so good. We can describe this explicitly as dependent of the electron density, right? But what happens with the kinetic energy and the electron-electron interaction? This term of the total energy cannot be written explicitly in terms of the electron density. So what we do is we keep it just written in this way. Some of you I saw they had the written the nabla, basically the expression of the kinetic energy operator, which is -1/2 nabla. So that's good. The answer only missed this part, which is the complex conjugate to take the expectation value, but it was a good idea. And the other one was missing the kinetic energy operator. So far, so good. Now, this one, I couldn't see well the answers, but I think you also wrote that it was the expectation value of the of the potential operator, and which is good. That's good. Is it? So what we have discovered, and you have already thought, is that we cannot write these functionals in terms of the electron density. Okay. So what can we do with the Hohenberg-Kohn theorem? Basically, this theorem is telling us that we can extract all the information from our system just by using the electron density instead of using the many-body wave function. So we're reducing the complexity and the multivariable problem to a easier problem to solve. So we're able to tackle and solve for the properties of a system. So I'm sorry, I'm gonna go back again. But still, we need to find the functionals that depend on the electron density, right? And turns out that the most complicated functional to find is the kinetic energy and the electron-electron interaction. But to tackle the part of the kinetic energy, Kohn and Sham proposed the following system. Instead of studying the real system, the interacting electron system, they propose a system of non-interacting electrons. So what are the properties of this system? First of all, our electrons are not interacting at all. but they experience an effective potential, which is called the Kohn potential sometimes, or effective potential. And in this presentation, we're going to call V sub S. That's the effective potential. This system has exactly the same density as the density of the interacting system. In the interacting system, as we can see in this picture, the electrons are all interacting between them, and they're experiencing an external potential, which is the electron nuclei potential. So this external potential and the effective potential are completely different. The effective potential for the Kohn system are completely different in order to get the same exact electron density for both. So in the Kohn system, what we have is that each electron, because it's independent, it's related to a one-particle Schrödinger equation that we have written this equation in this slide. We have the Kohn operator, single Hamiltonian, single particle Hamiltonian of the Kohn system. We have the psi I, which are the Kohn orbitals. That's how people call them, or one particle orbitals. And we have the eigenvalues and, well, Kohn orbitals again. This is a Schrödinger-like equation where the Hamiltonian of Kohn it's given by the kinetic energy operator and this effective potential that I just mentioned. Using this Hamiltonian, we can get the Kohn orbitals and then compute the total energy of our systems. Okay. So we've mentioned this density has to be the same. Both of these external potentials that are different lead to the same density that belong to both systems. So they have to be different in order to give the correct density. Now, with this, we can explore more properties, or we can access to other properties, such as the kinetic energy, right? So we have said that the total energy of the total energy of our system is a function of the density, has the kinetic energy, electron-electron, electron-nuclei, nuclei-nuclei. So we know this. Now for the Kohn system, because we are removing a very important part of the real system, which are the interactions, we need to account for this in the total energy. And we have to incorporate the exchange and correlation. This part of the functional contains what we have removed from our system. It describes the interaction that we have removed. Now, we also see that we have a different kinetic energy, which is Ts. This is the kinetic energy of the non-interacting electrons, which is not the same as the kinetic energy of the interacting system. This is given, as we see in this slide, is the sum of all the electrons in our system by taking the expectation value of the kinetic operator using the Kohn orbitals. Now we're not using the many-body wave function. We're just using the Kohn orbitals. Okay. We have the Hartree term, which is the classical electron-electron repulsion written in this form. We have what we've discussed, the electron-nuclei interaction. Now, there's still something missing, right? Is the exchange and correlation. So with this challenge, you are gonna find an expression of the exchange and correlation in terms of the kinetic energy, the electron-electron interaction, non-interacting kinetic energy, and the Hartree energy. So please go ahead and start solving for this. You might want to refer to this slide to find the solution. So I'm gonna keep it. I'm gonna first let you do this.
If you can send the link in the chat, Okay.
Sure. Okay. Oh, no, but that's for the collaboration, not for the challenge.
Thank you.
Yeah. For this one, since it's, I think, a bit easier, you're gonna have only 3 minutes. So at 9:55, we discussed, okay?
Please, can you go to the last slide?
Yes. Here it is. This one, right?
Yeah, thank you.
Mm-hmm.
Very challenging.
How many answers are there? 8 answers. Okay, this is good. We have 8 answers. Let me see what. Okay. So I see that most of you have a really good idea of what the exchange correlation is. So now let's try to make sense of this answer, right? This is the solution of the challenge. We have the electron-electron interaction minus the heart rate energy plus the total, the kinetic energy of the real system minus the non-interacting kinetic energy. So we already, with this equation, we could already see that, oh, we're basically counting for all the terms that are not included in the non-interacting terms, right? So we have, yeah, this is what you just mentioned. We have the non-classical electron-electron energy that we're missing, which is basically this one, the electron-electron minus the heart rate. This is the exchange plus correlation term. And then we have the kinetic correlation, the part of the kinetic energy that the non-interacting system cannot access, okay? Now, the exchange correlation energy, it's very in percentage in comparison to the total energy, is very small, usually 10% of the total energy, but it's very important. If we don't include this exchange correlation, we are not able to study bonding systems. So that's why most of the, a lot of the research in DFT is to find the most accurate as possible exchange correlation functional. And there are many flavors. So let's discuss how this can be approximated. So let's see the The exchange and correlation energy can be divided into the exchange part plus a correlation part. In Hartree-Fock, we are able to access to the exact to the exchange energy, but in DFT we combine these both to access them through the electron density, not the single particle wave functions. So one of the simplest approximations is the local density approximation, which is exact and very accurate for uniform electron gas systems. So for systems where the density is homogeneous, and this is the expression for that. And it's an example of the Dirac exchange. However, this fails on describing real systems because we're basically missing a really important part of the term, which is the correlation. So there's many flavors of exchange and correlation functionals. I'm sorry, I said something. The LDA is really good approximation. You can use it to study many systems, and it's cheap. Okay. Now there's many different approximations for the exchange and correlation, as we have mentioned. We have this very famous Jacob's ladder. So in this case, the Jacob's ladder is upside down, but we will start with the LDA, which is the most, is a local density, it's computationally cheap, but it's not super accurate for systems where you want to study very inhomogeneous densities. Now we have the generalized gradient approximation. In this case, we add the gradient of the density. An example of this is the PBE functional. We have meta GGS. In here, we add the kinetic energy density. An example of this is the scan. This is a bit more computationally expensive because you have to add the single particle wave functions in the evaluation of the functional. Then we have hybrids where we combine the exact Hartree-Fock exchange, and then we combine these with a functional such as PBE to incorporate the correlation. And then we have full non-local functionals such as RPA or double hybrids. This ladder, as you go up, in this case you go down, the accuracy increases, but the computational complexity and cost also increases. So the efficiency decreases. Now, yes, we've discussed that. Now, one of the examples and tutorials that you're gonna be working later with is QEPI. In QEPI, you can select what exchange correlation functional you want to use in the same way as QE. So QEPI is a Python interface that connects to QE. It uses all the engines from Quantum Espresso. So you have the same keywords for the input files in QEPI as in QE. So you have the system and you have the input DFT. This defines the exchange and correlation functional that you want to use, in this case, LDA. Usually, you do not specify this part because the pseudopotential file, which you will probably hear about these pseudopotentials, contain already the type of functional that you're going to use for your calculation. So if your pseudopotential was optimized for an LDA exchange correlation, your calculation is going to use LDA. If your pseudopotential was optimized or generated using PBE, then your calculation is going to immediately take the PBE exchange and correlation functional. Okay? Now, an important part for theoretically for solving the electronic structure is to find these Kohn-Sham orbitals, right? We want to find the orbitals that lead us to the ground state electron density. How can we do that? To do that, we're gonna describe or formulate a Lagrangian with a constraint. So Lagrangians help us to find the minimum of a system, the ground state energy of a system, right? So we have the total energy that depends on the Kohn-Sham orbitals. We see that it does not depend explicitly on the electron density because the kinetic energy has to incorporate the Kohn-Sham orbitals. And we add a constraint. The constraint is that the Kohn-Sham orbitals must be orthonormal. So basically, this epsilon is like a Lagrange constant multiplier, like a Lagrange multiplier. So one way to find the minimum, the wave functions that minimizes the energy and lead us to the ground state density is by taking the functional derivative of this Lagrangian and equate it to 0. One important note is that we have to choose the canonical orbitals, meaning that they are diagonal. So they're just a matrix that is diagonal. So we can take the functional derivative with respect to the complex conjugate of the Kohn-Sham orbitals, or just reading the same idea just in Dirac notation. Let me zoom in this. Okay. Now this is gonna lead you to the Kohn-Sham equations. This is the Kohn-Sham equation that we saw at the beginning, and this is the way we get to the Kohn-Sham equation by taking the derivative of the Lagrangian. We have again the effective potential for the Kohn-Sham system, the Kohn-Sham orbitals, kinetic energy operator, and the eigenvalues. So in this case, we wonder, okay, so we've done this. So what is the effective potential? We have been talking about it, but we haven't really defined it or given an explicit form of this effective potential. So that's going to be your challenge 4, and it's a homework. You're going to need to know what is the chain rule of functional derivative. This is the normal formulation of the functional derivative. And this is the expression that you have to show. You need to demonstrate that by taking the functional derivative of the Lagrangian, you get to first the Kohn-Sham equations, and second, you find the explicit form of the Kohn-Sham potential or the effective potential. Now in here, you're gonna have the derivative of the Hartree potential, the exchange correlation, and the electron-nuclear interaction. Just leave as it is this expression of the exchange correlation. Since we don't know the exact form, you can use the LDA and try to take the functional derivative, or leave it just as it is, like an expression. And then you're gonna also find the derivative of the Hartree functional. With that, I think we finished part 1, and I will let Fabrizio to continue with part 2, which are basis sets, and he's gonna explain. How you're gonna do it? Aniket is gonna do it. So he's gonna tell us, okay, how can we then represent the Kohn-Sham orbitals in a computer, right? So
yeah, so until now we saw the equations and we saw what the equations give us. We can solve for the electronic structure using those equations, but how do you do that on a computer? And for that, we need something called basis sets. And so before we dive in, we're going to make some basic assumptions about what you guys know. We like basic linear algebra and then Dirac notation, and we discussed Kohn-Sham equations and everything. So we're going to base our talk on those assumptions. And so the first question is, why are basis sets needed? So the main importance for basis sets is that they allow us to discretize the problem. They allow us to break the problem into small parts, which the computer can then solve. And so how do we do that? So the first thing is we choose, we can expand our wave function in a basis, like a sum of a fixed function, and each function has its own coefficient. And so we can expand that. We can break down our Kohn-Sham or Kohn-Sham wave functions into a basis. And these collection of basis functions are called a basis set. And the CIK terms are the expansion coefficients. And so by analogy, this is like the sum of a vector, the components of a vector along the basis vectors. And so then any orbital is a weighted sum of the fixed building blocks chi I. So these are the fixed functions, and they are weighted by the coefficient C. And so this turns picking a basis into finding a function that can describe that basis into finding the numbers CIK and keeping the function part constant. So the coefficient CIK is something that the computer can solve for. And so what we end up describing our electronic structure. We transform it from a single from like a collection of wave functions into these sum of functions, which each sum has its own coefficient, and we solve for those coefficients. And once we get those coefficients, we can accurately describe our wave function. So what are some examples of basis sets that we use in our day-to-day DFT calculations? So one such example is a plane wave. The plane wave has it's a bit complicated, but it's one way of describing how an electron flows in any kind of molecular system. It's mainly aimed at describing solid systems or systems which have like condensed phase, which have the repeating units, and so we'll discuss why plane waves are used for solid systems. And another such basis set is a Gaussian type orbitals. Now, if you can see the function form, they have both exponential functions, but they are described differently. And that leads to their different behavior, and we get different types of challenges when you use either basis set. We'll discuss that in the next few slides. There are some other ways of describing basis sets, but primarily the plane waves and the Gaussian type orbitals are the two most commonly used ways of describing the electronic wave function in an electronic structure problem. And so what do they look like? So yeah, this is where the big difference comes. So we have a small Python code which gives us the description of how these plane waves and Gaussian type orbitals look like. So you have the position of the ion in the center, and so you can see that the Gaussian type orbital has a fixed peak, whereas the plane waves have this flowy wave-like motion. And there's a reason why there's a difference in the way that they are describing the same ion, and that difference is okay. I missed it. That difference is why they are used to solve different kinds of problems. So the plane waves are delocalized and periodic, which can be used to describe solids, which are also periodic, and they have a fixed structure which is repeated infinitely in all directions. Whereas Gaussians are localized on atoms, which are well suited to describe molecular systems, which have a fixed set of atoms in some kind of fixed order, and there's no periodic structure. And so that's why there are these two ways of describing your electronic wave functions, and DFT can use both. And so that leads us to our next challenge. So are these two representations of these wave functions, are they orthogonal? And if you calculate their overlap matrix, what do you get for the plane waves and for the GTOs, and why? And so this is a bit complicated, or this is a bit more involved. So you need to think about it. So maybe take 8 minutes. It's a weird number, but yeah, 8 minutes to just see, and we'll discuss the results afterwards.
Hello. Can you go back to the previous slides, please?
This one?
Yes.
Okay, yeah. So we saw a few of the responses, and yeah, it's a bit of a mixed bag. So how do I? So okay, so the plane waves, so they are orthonormal, and that's because of how they are by design. So that G term in the exponent, that's the reciprocal space vector. And so won't go too much into detail. Basically, since plane waves are applied to solids, they are described in the reciprocal lattice vectors of these solids. And so by design, the overlap matrix is a Kronecker delta. And when the two G vectors are the same, the integral gives 1, and otherwise it's 0. And so they are orthonormal. However, the Gaussian type orbitals, since they have a different, their form is different, a product of two Gaussians is another Gaussian. And so the integral is always positive, and it only vanishes when the two centers are infinitely far apart. So they are not orthonormal by design. However, because of their design, and to use Gaussian type orbitals to solve any kind of electronic structure, solve the Schrodinger wave equation in the basis of Gaussian type orbitals, they need to be orthogonalized. So yeah, so the solution is that plane waves are orthonormal. Gaussian type orbitals are not. Is there a question? I'm sorry, is there a question? Okay. Okay. Yeah, feel free to ask questions if you guys have any. And so we'll discuss the plane waves a little bit more. And so as I said, these basis sets are like these sums of functions with fixed weights or coefficients on each function, which collectively describe a density or some sort of wave function. And so how many of these functions are needed to get an accurate description? And so in QE pi, there are these two parameters, E or QE, there's two parameters, E cut wave function and E cut rho. And so these kind of decide the accuracy of the plane waves. And so it depends based on what pseudopotential you're using. And so I won't go into too much detail. Basically, we can, the more complicated the target density, the higher the number of plane waves that you need. So for example, over here, you can see in this plot, the black, the density plot is kind of overlaid on underneath the green plot. So if you increase the number of plane waves, you get a better description of the target density. And for too few plane waves, you get these ripples, and you can't resolve the actual feature. And so these sharp peaks need a higher E-cut wave function. And so that's exactly what these cutoff parameters control. Depending on what kind of pseudopotential you're using or what kind of system you're using, you can play around with these cutoff parameters and get the accurate representation of the target density. And so yeah, so now we have a very small challenge. It's I kind of went a bit fast through the plane wave. So if you guys have any questions, feel free to ask. The next challenge is just a unit conversion. So there are three primary units that we use to describe the energetics of these systems. So it's either atomic units such as Hartree or Rydberg, or electron volts. And so converting in between these units is very common in any kind of electronic structure problem, especially if you're doing things like excited states. And so, yeah, this challenge is like, it's basically an atomic units conversion. So it's really useful to like keep in mind what these conversions are, so that you don't have to look them up every time. But yeah, these are pretty common. So yeah, I'll give like 2 minutes, and then we can go to the next part.
If you can.
But they want the link to the challenge.
Oh, the link. Okay.
Yes.
I'll share the link.
I have it.
Okay.
Okay.
So I would say while we wait for the people who do the form, also, if there are questions, obviously you can feel free to ask.
Okay, I think that's enough time for that challenge. It's pretty straightforward. So yeah, from here on, I'll hand over to Fabrizio. No. And he'll start talking on how do basis sets discretize the Kohn-Sham equation. I'll stop sharing, and Fabrizio, maybe you can share your screen.
Yes, I will share my screen.
Okay.
Can you see?
Yes, we see your slides.
Okay, perfect. So until now, we've talked about what DFT is and how do we okay. We talked on one side what the DFT is, on the other side what is a basis set. But then what we have to do is we have to use these basis sets, which are basis functions that we use to express the electronic states, to actually solve the Kohn-Sham equations. So this is what we will be talking about now. So sorry, this went too fast. Okay, this was, I don't know if we have time to actually stop and like, how do you say, dividing groups. I don't know if you can tell me about it, but
What do you suggest?
we can, because I mean I know that oh, zoom in, yes. Sorry. I don't know if you can see the equations. Can you see the equation well?
Yes.
Is it big enough? Okay, good.
Yes, I see.
Okay. The plan here would be to have the students actually write the equations. These are the Kohn-Sham equations that we worked on until now, and to express it in terms of the set of plane waves or basis functions, whatever they are. But I don't know if we have time for it. What time is it? 10:30. If we want to finish within 2 hours, then maybe we can go past, because it would take some time.
Okay, we can try to divide them as you suggest.
Otherwise, I will go forward, and then in case we can do it later.
Okay.
They can do it as a homework, let's say.
Yeah,
So
I think
okay.
there are some homework problems which discuss this, but yeah.
Okay, good. So these are the Kohn-Sham equations. So we have the defined in terms of the how to say, sorry, the state of each electron, these phi k's. But we want to discretize them in terms of the plane wave that we were that Aniket was talking about before. So how do we do that? What we do is we express each Hamiltonian. Okay, let me go back. We express each Hamiltonian in terms of its matrix elements, so its interaction with each basis function. We express each orbital in terms of a set of basis functions time multiplied by their coefficients, so a linear combination of basis functions, and we express the overlap elements among the basis function as the bracket chi j chi I. So what we get is that we get a set of equations in which that can be expressed in matrix form as HC equal SC epsilon, in which basically every Hamiltonian, the Hamiltonian of each, the matrix element of each orbital is summed over all the basis functions. So in this case, in matrix form, which is a little bit easier to understand, we have H, that is the Kohn-Sham Hamiltonian, so the mean field Hamiltonian. C is the matrix of the coefficient, in which each column represents a Kohn-Sham orbital, and obviously the rows of each column represent the coefficients for each basis function. In plane waves, these are simply the bands of the electronic structure. Epsilon is the diagonal matrix with the orbital energy, in which each orbital energy is the Kohn-Sham eigenvalue, and S is the orbital overlap matrix. Obviously, because plane waves are orthogonal, the matrix is diagonal. But in the case of GTOs or atomic basis sets, there is overlap between the basis function. So obviously the matrix would not be diagonal, which complicate things a little bit. So how do we solve this? Because the idea of having this is exactly to have something that can be solved. Basically, the way we solve this is by remembering that each hij is a functional that we can express, and so that depends on the number of. Okay, sorry. Let me. Okay. Sorry, I got a little bit confused. I thought that was later. So the point is, okay, yes. The point is we cannot solve this directly because the terms of the Hamiltonian obviously are the terms of the Hamiltonian that we were talking about before, and those depend on the electron density. But how can we solve the electron density? How can we solve the orbitals that depend on the electron density if we don't know what the electron density is? So this is a recurring problem. So the reason why we call it we use what's called an SCF cycle, so a self-consistent field cycle, is to solve this equation in a way that gives us both the orbital energies and the electron density. So this is called a generalized eigenvalue problem, which you can read about more if you have the slides. And the base of the problem is, as I was saying, that H, so the Hamiltonian, the matrix form of the Hamiltonian, depends on the external potential, but the external potential depends on the electron density. So what electron density can we use to evaluate H? The point is we can have different options. We can start from a uniform density. We can start from a sum of atomic densities. But the point is, whatever choice we make, we have to start from a guess of the electron density to evaluate the external potential and the Hamiltonian, so the orbital energies, to obtain something that is to obtain then a new electron density and then repeat the cycle, and that is the self-consistent cycle. Because if we start from a sum of atomic density, obviously that's only a guess. So what do we do? As I was saying, it's a chicken and egg problem. To build the Hamiltonian, we need the density. The density comes from the orbitals, and the orbitals come from solving the discretized Schrödinger Kohn-Sham equation. So, as I guess I was saying, the only solution is a self-consistent solution that gives that has this iteration: guess, solve, rebuild, repeat, until we have a solution that is stable. So what is the self-consistent loop? The self-consistent loop is, you can find it here, is you start from an initial guess for the density, which is usually a sum of atomic densities. We evaluate the Hamiltonian, so the Kohn-Sham equation, the discretized Kohn-Sham equation for that initial density. By solving, we solve then the discretized equation to obtain the orbital energies and orbital parameters. With those orbital parameters and orbital energies, we build the new electron density, which will be different from the original electron density, will be better, will be closer to the original. And then we evaluate the difference between the initial guess and the new output that we have. If the difference is 0, it can never be 0 because we're using like a finite precision computers. We don't have access to infinite precision computers, unfortunately. But if the difference is smaller than what we consider to be our target, then we say, okay, then this is the correct one. If it's not, then we use the output density as the input to evaluate the Hamiltonian, then to solve the discretized Kohn-Sham equation, and then build a new output density. And then we repeat and repeat until we find something that we find a new density that is almost the same. Again, we will see that this tau is actually, it's very important to choose it wisely, but a density that is almost identical to the previous density, then we say that we have actually solved the Kohn-Sham self-consistent loop. So what does convergence look like? Because obviously, as we said, it's an SCF cycle, so it will converge in one way or the other. How do we know if we're going in the right direction? The problem here is that which we can express, we can show with a little Python graph, is that normally convergence might not converge at all. So if you run the SCF loop normally without any improvement, without any extra parameters, what you might have is that the output density is very different from the input density, and it does not give you a direction to how to improve it, or it might actually be worse than the input density. So the trick that is usually done is called density mixing, in which is in this case the orange line, which basically mixes the output density with the input density in a way that allows us to converge the SCF very fast, very quickly, so with just a few iterations, and also in a much more stable way, so without the risk of diverging SCF loops that would basically just, you would just keep computing and computing and computing without getting anywhere. What is density mixing? Density mixing is, as I was saying, mixing the input. So you have that the new input, density is a certain beta of the output density of the previous calculation plus 1 minus beta, so of the input density of the previous step. So beta is generally a mixing parameter, which can be usually changed in pretty much any quantum chemical program. In the case of quantum espresso, it's expressed in the mixing beta, with the mixing beta parameter. I think it's about 0.7 the default for quantum espresso, and that is a good starting point, but you might need to change it if the convergence doesn't work very well. So it damps the oscillations as we were saying before, it avoids those massive oscillations between those massive changes between input and output, well, between the densities at different steps. So it stabilizes convergence. Then there are different other schemes that are a little bit more complicated, sometimes a lot more complicated than this, that can stabilize and accelerate the convergence even further. The IIS is the most commonly used. So good mixing can turn diverging SCF into converging SCF, which makes the SCF Kohn-Sham SCF actually usable. Here I will actually explain the basic workflow for quantum espresso and QEPI that you will actually see in detail during the tutorial. Sorry, during the hands-on session. We handle the SCF cycle in the card and control, which in QEPI, if you're using QEPI, is a dictionary. So in which each so the QEPI option, sorry, the QEPI and control card is a dictionary, as you see here, and then each of the sorry, what's the word? Parameters. Each of the parameters of the N control card are an item of that dictionary. So in this case, for a simple SCF calculation, the calculation key is SCF. As I was saying before, one of the most important parameter for the SCF cycle is the SCF threshold, which is usually expressed in units of energy. This unit, can you see? Is it big enough? Is it small?
Maybe if you can increase it more, it's not.
Is that okay?
Yes, perfect.
Okay. So there are different conditions that can be used for the self-consistent threshold. The simplest one is just the integral of the density difference in all of the unit cell space. Quantum espresso uses a slightly more complicated one, which you can find here, which uses the two density differences in two different points, so like a double integral. But they are obviously how do you say? They will have different values, but they serve the same purpose. To verify that you understand this, on top of what we said before, to discretize the Kohn-Sham equations, what you can also do is to derive the equation to obtain the electron density from the basis functions and the wave function to coefficients by using the expression that the electron density here, NR, is equal to the sum of the square moduli of the orbitals. Obviously, what you have to do is, as you did before in terms of the discretizing the Kohn-Sham equations, you have to substitute these orbitals with the plane waves and the coefficients. It's actually a relatively simple problem. I'm sure you can do it. with this, we conclude the part on the self-consistent field, and we start talking a little bit, because I know you will have a different session on band structure, but we will talk a little bit about band structure and specifically occupation numbers. The usual equation that we talked about just before is for the electron density, says that the electron density is the, as I was saying, the sum of the square moduli of the orbitals. What does that mean? That means that if the orbital is occupied, that will contribute to the electron density, and if it's not, it will not contribute to the electron density, because this summation is up to n, so up to the number of electrons. So as usual, we'll start occupying the orbitals from the lowest energy. We put two electrons of opposite spin in each orbital until we run out of electrons. The orbitals that we get from the discretized Kohn-Sham equation are a lot more than what is needed to obtain this to fill and to use up all the electrons. So only the occupied orbitals actually matter for the electron density. However, for this is only true, the Aufbau is true in the case of zero temperature, or better, it's strictly correct. In the case of a non-zero temperature or for small band gaps, what we have is that we have to add a term that is called the occupation numbers. So rather than having either a 0 or 2 occupation for each orbital, so other than adding the electrons one after the other, we will see that we can have fractional occupation numbers. This is a typical case. The typical case, obviously, is for metals that don't have a band gap. So the orbital energies overlap between around where you're supposed to stop in adding electrons, and therefore you have to use fractional occupations. Sorry, I have to. For solids, because we use K points, we haven't really talked about K points, but because we have to sample the electronic structure in different points in the reciprocal space, we have to do something that is called smearing, that basically will how do you say, to express it in very simple terms, it mediates between the K points in a way that allows us to sample not just the positions in reciprocal space that we are looking at, we're actually calculating with those K points, but actually we can sample also the other points that are in between. So I don't know if I should go on, Aniket and Valeria. Like, what do you think? Should I keep going, or
I think
should we end it?
There's a small example in the next, or maybe this slide, that shows the effect of smearing.
Yeah. Okay, should I end it? Okay, yes.
Yeah.
What is this smearing? Basically, when you consider a set of eigenvalues coming from the Kohn-Sham equations, if we don't have occupation numbers, what we'll have is that the occupation is 1 until the Fermi energy, which you can see here at the dashed line, and then 0 afterwards. As we increase the smearing from 0 to 0.1 to 0.5 to 1.5, what we see is that we change the distribution of the electrons to include more and more of the orbitals above the Fermi energy. So to put it all together, obviously this is, I understand that this is a lot of concepts. I don't know if you can read properly. What we discussed is the how to solve, okay, the Kohn-Sham equations. So how to actually get results that are meaningful from a geometric to solve the approximately solve the Schrödinger equation for a given set of atomic positions, basically. So obviously we have to start from the geometry of our molecule or our solid, choose a basis, so choose a pseudopotential, or should you talk about molecules, Gaussian type orbital, and cutoff, which tells us how big our basis set is, and therefore guess how to say electron density based on our pseudopotential or basis set. Make an SCF loop, run through an SCF loop. So we build the Hamiltonian, we solve the Kohn-Sham equations, we occupy the orbitals that we've built, either in the case of insulators, we just occupy the first using just the number of electrons, or in the case of metal, using occupation numbers. We build a new electron density. We use different mixing schemes to guarantee convergence, and then once we reach the convergence threshold that we decided, tau, we say that we have a converged electron density, and from there we can again build the Hamiltonian, this time instead of to run another SCF loop, to evaluate the energy, the forces, band structure, every other properties. So basically everything we talked about since Aniket started talking, basically it's just one SCF loop and one pass around the SCF loop. And this concludes, I think. Oh no, sorry. No, this concludes. So this concludes the presentation. You will have an hands-on session, which is called SCF with QEPI, in which you will actually build an SCF loop using Python. I don't know if we want, I'm asking the organizers if we want to discuss the hands-on session, or obviously if there are questions, please feel free to ask.
I have a comment related to
Mm-hmm.
the hands-on sessions. Um, I think if you want to give just a brief summary about what these hands-on sessions about, because
Yeah.
we're gonna do the hands-on session schedule actually for tomorrow. We're going to
Okay.
use like similar materials that you've shared with us for the participant
Mm-hmm.
because they haven't yet started hands-on sessions. So we're gonna
Mm-hmm.
start it tomorrow. But if you can give
Okay.
like a brief summary about what this hands-on session is gonna be about, it would be perfectly fine.
Okay. Yes. Absolutely.
Actually, I have a questions, and also if someone else also have a question, please feel free to ask. Related to the smearing, I have seen in
Yes.
literature, especially for the transition metal nitride,
Mm-hmm.
um, these systems actually are metallic, like niobium nitride, titanium
Mm-hmm.
nitride. But people, when they study the phonon properties, some of them they're showing unstable phonon modes. And then in
Okay.
some paper, I have seen people they increase the smearing widths in order to make the system stable. So, and the justification was increasing smearing, you increase the temperature or you increase the energy widths around the Fermi level. I didn't get
Mm-hmm.
it actually quite right. Do you have an idea or any comment on these, like to increase the smearing to stabilize, to make the material stable, or what's really happening? The system is still metallic, whether you use small smearing or large smearing rates.
The system is still metallic. The difference is it's the electronic temperature. Uh, in theory, at like pure 0 Kelvin, you wouldn't need smearing. You would just get the Fermi level, even in a metal. It's actually well defined. At any finite temperature, even 10 to the minus 5 Kelvin, you will have a Fermi Dirac distribution of electrons around the Fermi energy. The higher the smearing, so actually that's why the smearing is expressed in terms of KT. So it's in terms of like the constant, like the units are the same as the Boltzmann constant times a temperature in Kelvin. I honestly am not an expert in TDDFT, so I don't know specifically in the case of phonons uh, why increasing the um, uh, the smearing will make the system more stable. I don't know if Valeria, who's done more work than me in TDDFT, knows this, but it might just be how do you say, kind of a computational trick.
Yeah.
Because what I found is that in the case of metal, especially magnetic metals or systems with um, especially systems with transition metals, uh, increasing the smearing can help convergence in general, even in ground state DFT, because it smooths the pretty much smooths the electron density as well, because it prevents the formation of very hard features, like very very uh, yes, I don't know how to say, like very narrow features that are difficult to express in terms of plane waves. As we saw at the beginning, the harder the features, so like for very narrow features in the electron density, you need a higher cutoff. those are generally dependent on the elements that you have in your system. But not 100% exclusively. Like the different, especially complex materials. Like for example, when I was working with NMC cathodes, I encountered this, that the different magnetic behavior of different transition metals can make it difficult to achieve some convergence, and the smearing can help. But I don't know specifically in the case of DDDFT, unfortunately.
I see. Okay, no worries. Thanks.
Okay. Any more questions? If not, I can go through the tutorials. I will send the link here in the chat.
Okay, so I will stop sharing.
Okay.
Yeah?
Yes. And I
So you
will.
can share your screen.
Thank you. Just the red button, it says stop sharing.
Yeah, stop share.
Yeah.
Thanks.
Yeah.
Sorry.
So I'm gonna open this. So this is the link I sent you. We have different tutorials on how to use QEPI to perform the SEF calculation, relax a structure, equation of states, or molecular dynamics. So since in this presentation, we only show you the self-consistent field cycle, so let's just do the tutorial for the SEF. You're free to try doing the other ones. It's useful for, it might be useful for your research. So what we're gonna do, you're gonna open this link and we're gonna work in Colab. This is because it's very easy to use and to install programs. So in here I have uncomment the following lines for Colab. So it is very important for you to first install QEPI in this way. So you're gonna click here. If you haven't used Google Colab, you just click this button and that's gonna run that cell. In here you're gonna put run anyway. It's gonna take like few seconds, hopefully, and then it's gonna pop up another window and you're gonna restart the kernel. So it's gonna ask you immediately. So let's wait for this. Ignore that and then just restart session. Then it does immediately. We're gonna install Potly as well. And we will also uncomment this installation and we're gonna run this one. Once this is done, we run this one. And these are some important functions that we're importing from QEPI. So we have the QEPI driver, QEPI input. The QEPI driver is like the engine that performs all the calculations that you want to do, like the SEF calculation or the relax calculation or phonon calculations. The driver is going to perform all the calculations you want. It already contains all these algorithms that we discussed, such as the SEF. This is just and then we have the QE input. This is to write the input file for QEPI. We have SC, which is Atomic Simulation Environment. This is to build molecules or systems. In this case, we're going to use a bulk. Then we have the normal NumPy. We have Matplotlib, which helps us plotting stuff, and Plotly, which is a Python package that also helps us plotting 3D functions. In here, you're gonna run, so don't forget to run all the cells. If you don't run this a cell previously, like if you don't run this cell, this is gonna fail most probably, because you need to import all the functions that you need from these Python packages. So in this download file, it's gonna download your pseudo potential file, and you can see in here, we just downloaded. We didn't have it before, so you can get it. This is a DFTPy function. You build your system. This is the prefix you're gonna be using. As in QE, if you have run a QE calculation, you need to define a prefix to label the calculation so you can read all the outputs while you are running your calculation. We have your SCF options, is a dictionary, as Fabrizio mentioned before. You have these keywords, they are exactly the same as the ones as in QE. So you can go to pw.x and that's gonna tell you each what each keyword means in QE, and you put it in QEPy as well. So you run this, you define what system you want. So in this case, we will define first the ECOT, the convergence threshold, the pseudo potential files, the atomic mass, the type of material that the type of element that is included in your material. Since this is a molecule, we're only gonna use the gamma point. Again, this is we didn't discuss what are K points and what is the gamma point, so you should look into that. And then we already run this. It says here it's run. So this is the 6th one, and this is 0. We haven't run this. So now with ASE, we're gonna build this molecule. So ASE has a data set already. So if you put the formula of your molecule, it's gonna have it. If it doesn't have it, then you will have to build it yourself. You can also look into that, how to build molecules with ASE. So in here, it's because QE works with plane waves, we need to define a cell to define the range or the space where these plane waves are gonna live. So that's why it's very important to define a cell of our system, and then we just translate this. Why are we translated? Because we want the molecule to be in the center of the cell. Okay, you can also just do atoms.center. You don't need to put this one. There's different ways of using ASE. So this is one way. And then what we're gonna do is we're gonna print the SCF options. This looks exactly like an input file from QE. So then we define the number of bands. So we're gonna be using 10, and that's because we have 4 hydrogens, so it has 4 electrons plus the 2 carbon. How many valence electrons carbon has? You can put it in the chat. What are the valence electrons for carbon? Guys? I'll give you 5 seconds. If you don't answer, then I'm gonna let you look for that and think, why are we deciding to put number of bands 10? 1, 2, 3, 4, 5. Okay, so this is gonna be another homework for you. 12. Okay, so this is gonna be your homework. How many valence electrons carbon has, okay? And then you're gonna say, oh, so then why 10? So then now we're gonna build our driver, which I told you the driver is this magic class that contains all these algorithms that we're gonna use. So the driver, when we just called the SCF algorithm, basically it's gonna perform your SCF calculation, and it's very fast. You can already find this is the energy of the ground state. So it finds the density and it gives you the energy as well. So you're gonna save all your calculations. So when you do that, when you perform the SCF, you see that you have a temporary folder here, similar as you have in QE. This it's created because we're using QE. And this saves all the data that you have, the charge density data file, the wave functions, and all of that. So in QE, when you want to get the density, you have to do post-processing, and it's a bit annoying. But in QEPy, you can do it very easily. So you get the wave functions, or you can also get the wave functions. So in this case, what we're going to do is get the wave functions of K.0 band 4. So we said we have 10 bands. Now we're going to use only, we're going to get only the fourth band at the K.0, and we're going to take the real part. Now we're going to, because we want to write this in a 3D array, QE is going to give you an array or 1D array. So because we want a 3D array, we're just going to transform from 1D array to 3D array. This function does that, data to field. And that's going to be done. Now we can plot the density, the wave function, sorry. And these are the way, this is the wave function of the band 4 at K.0, at the K.0, okay? You can look at other wave functions, you can change that. And then your challenge for this tutorial is gonna be to plot the electron density. So you, from the driver, get the density, plot another Kohn-Sham orbital. So instead of choosing band equals 4, you choose any other number of bands. You can also plot the occupation numbers versus the orbital energy. What you should observe is like a Fermi-Dirac distribution, similar to what we observed. And the last challenge for this, is to do the same exact thing, but for another molecule. So you need to build another molecule with ASE. You need to get your pseudopotentials with ASE. These pseudopotentials, you can get them from Quantum Espresso. Okay, so just literally Google in Quantum Espresso pseudopotentials table, and you're gonna find a clickable table to download all these files, or to get the link like in here, and you just copy paste the link and you're gonna download this pseudopotential. Okay, you're gonna change your prefix, you're gonna change your molecule, depending, you keep the cell as 10 by 10 as we did here. So this is the tutorial to perform an SCF calculation using QEPy. Questions?
Participants, please feel free to ask any question about the lecture or about the tutorial. You can also write your question in the chat.
One that I'm showing here.
Anyone tried from the participant? Okay, there is a question from Dua Salim. She's asking, how do we make the first guess of the electron density?
Okay. Yeah, so Fabrizio mentioned that. So in here, for example, when we do this, the driver is gonna already take an initial guess, and you can take two initial guesses. It can be a uniform electron density, or it can be an atomic orbital density. So let me go to the presentation. Where is it? Where is it? Maybe I can just scroll
Yeah.
down. So this is what this is it. So these are the two options that we have, the uniform density or the sum of atomic densities. So QE usually does, no, this is for the treasure. So what QE usually does is the sum of atomic density. So it takes the densities that are in the pseudopotential and mix them. So each file, for example, we have two hydrogens. This hydrogen, you can get a pseudopotential, and that pseudopotential is gonna have a initial density or like some sort of density. Okay, and then you add this one and add the three of them, and that's gonna be the initial density. Now, if you use QE pi or QE, you don't have to specify it because the code is gonna do it for you. It's gonna take your system and it's gonna immediately create your initial guess. And this is what QE does. Okay, sum of atomic densities. Now, your second question is the electron density a measurable quantity? Yes, you can measure the density. So you can take the, basically the density is an observable.
Okay.
Yes, it's an observable and you can plot the density. You can observe the density as we are observing these orbitals over here. That's gonna be your one of your challenges. You're gonna work on this tutorial and plot the density. And that this density is a measurable quantity, basically. It's unobservable, okay? That's why it's also very good to work with densities. So you can see the value of this density on each direction, X, Y, and Z. So for example, here the value is 2.02, okay? The density is gonna tell you the probability of finding an electron in space, right? So the higher the higher the value, the higher the probability of finding an electron in that range of space. So when you plot your density, you can look at that and you say, oh, where do I have a higher probability of finding that? Now, this is an orbital, so this is not going to tell you the probability, okay? But when you plot the density, all the values are going to be positive, and some of them are going to have a higher value, and some of them are going to have a lower value.
Okay.
Mhm.
Any other question? If there is no question, Valeria, do you have something to add or you finished?
No, I finished. This is the SCF calculation. This is the challenge. And feel free to do the other tutorials that are in the GitHub link that I share if you want to perform any calculations. Like
Tomorrow morning we will have the hands-on session and then we will work it with the participants.
Okay.
Okay. Thank you so much, our speakers, for today. And for the participant, tomorrow we'll have the hands-on at 9 a.m. Khartoum time. And we will also at 3, we'll have a lecture at 3 tomorrow. So thank you so much, Valeria, Anikit, and Fabrizio for this lecture. And it was a pleasure to have you with us. Thank you so much. Goodbye, everyone.
Thank you for having us. Have a good day.
Thank
Good
you.
day.
You too. Good
Bye.
day.